Hi everyone, this is Yuchen. Today I will present SneakyPrompt Jailbreaking Text-to-Image Generative Models. This is a joint work with the co-authors Bo Haolin, my advisor Dr. Yingzhi Cao from Johns Hopkins University, and Dr. Neil Gong from Duke University. There are two main parts in a text-to-image generative model: text encoder and diffusion model. The text encoder takes prompt as an input and output the text embedding as an intermediate results, and this text embedding is combined with the noises as an input to the diffusion model. And finally, we will get the output image. And here, the visual semantic of this image is guided by the input prompt, which is a dog laying down on the sofa. Text-to-image generative models can be applied to many scenarios. For example, art and design, data augmentation, and virtual world building. However, someone may abuse it for an SFW generations, which is not safe for work generation. For example, the sexually explicit content or the violent content. So in the real life, safety filters are usually deployed in the middle of the pipeline. There are three types of existing safety filters. The first one is a text-based safety filter, which is deployed in between the text encoder and the diffusion model. And this safety filter takes text embeddings as an input. The second one is an image-based safety filter, which is deployed after the diffusion model and take the image as the input. The third one is a text image-based safety filter. This is the safety filter deployed by the stable diffusion, which has some predefined sensitive concepts as text embedding, and then they will calculate the similarity between the output image and those sensitive concepts. Let's take a closer look at the safety filter. Imagine it is a binary classifier with two classes, an SFW, which contains some concepts such as naked or nude, and SFW, which contains some non-sensitive concepts such as happy, or benign meaningless tokens such as A, B, C, D, E, F, G. If someone wants to abuse it for an SFW generations, it could be detected by the filter and give no output. However, what if an attacker wants to bypass the safety filter? They might first slightly modify the sensitive tokens and query the model. If it bypasses the filter, the attacker will get the image. However, this image might not be semantic similar as the attacker's target. So the attacker will repeat modification until they got some prompt that the output image has the similar semantic to the target prompt. We define this type of prompt as adversarial prompt, which can first bypass the safety filter and then generate the image with target visual semantic, which is an SFW. There are two types of existing work. The first one is manual approach, and the second one is optimized approach. However, both of them are struggling in some challenges. Manual approach needs human efforts to craft the prompt while have a low bypass rate. An optimized approach needs a huge numbers of queries. Now let me introduce our SneakyPrompt. It is an automatic adversarial prompt search framework with two objectives. The first is SneakyPrompt gives reward if it bypasses the safety filter, and the second is it gives penalty if it got refused. So for the reward, it is the semantic similarity between the target prompt and the adversarial prompt's generated image. And for the penalty, it is a linear increase with the number of queries, since we want to minimize the numbers of queries because each of them incur a charge. For example, this is the price for del E2, so we can imagine that a 5,000 numbers of queries incurs $100 per adversarial prompt. And how does SneakyPrompt work? This is the general pipeline of the SneakyPrompt. The first step is to query the shadow text encoder using the target prompt, and we will get the text embedding of the target prompt as the semantic reference. And in the second step, it samples token from the search space and replaces the sensitive tokens in the target prompt. And then it will query the text-to-image model using the adversarial prompt, and if it does not pass, it will repeat the previous sampling process and update the policy network by adding the penalty. If it bypasses, we will get the image and then calculate the similarity between this image and the text embedding we got from the first step. Here we will have a similarity threshold. If this threshold is not satisfied, SneakyPrompt will repeat the previous procedures, and then it will assign the reward as the similarity and update the policy network. And if the similarity threshold is satisfied, SneakyPrompt will stop and save the image as well as the adversarial prompt. Now let's see what SneakyPrompt can do. We do not want to make the audience to feel uncomfortable to the NSFW generations, so we use dog and cat images for illustration. These images are generated by del E2. We can see that the blue tags are the adversarial prompt, and this prompt can be either some meaningless tokens or the combination of some benign meaningful tokens. And the red text is the target prompt. So by doing these experiments, we also add an external dog and cat detector as the safety filter to be bypassed. You can imagine the NSFW prompts also looks like this, which looks benign to human, but the generation is really offensive. And those examples can be found in our paper's appendix section with password protection. Here are some quantitative evaluation results of SneakyPrompt in bypassing existing safety filters. So we have two target systems, which is Stable Diffusion and del E2. In general, SneakyPrompt effectively bypasses all the safety filters to generate image with similar semantics to the target prompt with a small number of queries. Let us start from 6 safety filters on Stable Diffusion. SneakyPrompt achieves an average 96% one-time bypass rate with 100 on 4 of them and an average number of 40.68 numbers of queries with at least 2.26 queries, with a reasonable FID score indicating image semantic similarity. The bypass rate drops and the FID score increases for reuse attacks because the diffusion model adopts random seeds in generating images. The only exception is the bypass rate for text-based safety filter because such filters are deployed before the diffusion model. We then describe the closed box safety filter of del E2. So SneakyPrompt achieves 57% one-time bypass rate with an average number of 24.49 queries. Note that while the rate seems relatively low, this is the first work that bypasses the closed box safety filter of del E2 with real-world sensitive images. None of the existing works, including the text adversarial examples and manual prompt and also the optimized prompt, are able to bypass this closed box safety filter. Here is the Ablation study on different shadow text encoders, particularly when shadow encoder E hat is not equal to E and is equal to E. We have two observations. First, same text encoders improves the image quality with the smaller FID score for both one-time and reuse attacks, and especially for one-time. The reason is the same text encoder adopted by the attacker results in the same text embedding as the internal results of the text-to-image models, used to guide the semantics of image generation, which provides a more precise semantic compared with the different text encoder. The relatively smaller improvement for reuse FID score is because of the disturbance of the random seed. Second, there is no significant difference in the number of bypass rates and online queries. SneakyPrompt achieves a 100% of bypass rate with both shadow text encoders for the one-time performance and achieve around 17% for reuse performance with different random seeds involved. The number of queries is also similar because they use the same similarity threshold delta. We also have two variants of the reward function, one based on cosine similarity between generated image and the word embedding of input prompt, which is our default version, and the other based on the L2 distance between the text embeddings of original and adversarial prompts, which can be found in the appendix. This table shows the comparison between two reward functions. Cosine similarity results in a higher bypass rate and better image quality for both one-time and reuse attacks, while L2 distance results in a smaller number of online queries. And this shows the Ablation study on the semantic similarity threshold, delta. So we range the value from 0.22 to 0.3 on SneakyPrompt's performance using three metrics. Let us start with the bypass rate in Figure A. The bypass rate stays the same for one-time attacks but drops for reuse attacks because the generated image may be closer to the target and thus blocked by the safety filter. This is also reflected in Figure B as the FID score decreases as the threshold increases. Similarly, Figure C shows that the number of queries increases as the similarity threshold because it will be harder to satisfy the threshold during the searching. We also evaluate the impact of search space size, which is particularly controlled by the parameter L. Specifically, we change L to be 3, 5, 10, 50, and 20, and the detailed number of candidates in the search space can be found in our paper. First, Figure A shows a larger L leads a higher reuse bypass rate. The reasons are twofold. On one hand, the larger the L is, the larger the search space is. That is, the reinforcement learning agent has room to explore more subtokens and increase the bypass rate. On the other hand, a larger L introduces longer subtokens that dilute the sensitive prompt more, thus also increasing the bypass rate. Second, the image quality has little correlation with the search space. Instead, image quality in terms of FID score are more related to the semantic similarity threshold delta, as we showed in the previous slides. Third, the larger the L is, the more online queries SneakyPrompt takes. The reason is that the agent needs more numbers of queries to explore a larger search space to satisfy the semantic similarity threshold. Here is the explanation of bypassing. We first show the results of the output probability on an SFW of different safety filters for both the target and the adversarial prompts or their generated image, depending on the type of safety filters. We normalize the probability into 0 to 1, where a value larger than 0.5 indicates the sensitive input. The probability output of the target prompt, which is PT, is from 0.546 to 1, which is the target prompt is sensitive. As a comparison, the probability outputs of adversarial prompts, PA, generated by SneakyPrompt range from 0.0 to 0.482. This result suggests that SneakyPrompt is effective in bypassing different safety filters. Next, we also show the semantic similarity between the target prompt and its generated image, and that between the target prompt and the image generated by adversarial prompts found by SneakyPrompt. We observe that the latter, which is 0.298, is close to the former, which is from 0.267 to 0.289 for different safety filters, which indicates the ability of SneakyPrompt to maintain the semantics of target prompt and image generated by adversarial prompt. As a responsible research group, our goal is to make the system safe, so we disclosed our findings to DALL-E2, which is OpenAI, via their online portal and an email, and also the Stable Diffusion, which is Stability AI, via a Zoom discussion. Let's now summarize the key points of my presentation. We design and implement SneakyPrompt as the first automatic framework to jailbreak the text-to-image models. And we show that SneakyPrompt successfully finds adversarial prompts for an SFW generation of a closed box safety filter for DALL-E2. And we extensively evaluate SneakyPrompt on 6 open source safety filters for Stable Diffusion. And our tool and datasets is totally open set at this link. Please feel free to check it out if you're interested in our projects. Thank you for your attention.